So yes, this is going to be a pseudo-random talk. I work with physics simulation software for medical applications. And the state of the art since the 40s and the Manhattan Project in this field has been Monte Carlo simulations, which is based on random numbers. And these algorithms are mostly implemented in C++ on CPU and GPUs. But computer programs can't generate random numbers because they are supposed to be deterministic, and random numbers are not. So what is random? And what is pseudo-random? Randomness is the lack of pattern or predictability in information. And pseudo-randomness appears to be random, but are produced by a deterministic and repeatable process. And we want different properties of random numbers, but these are the main, that they should be unpredictable, in the sense that you shouldn't know what the dice roll is going to be before you throw it. Independent, in the sense that it doesn't matter what you rolled last time, the dice should still be random. Unbiased, you should get equal amounts of heads and tails when you flip a coin, and evenly distributed. So yeah, it's the same probability to get a 1 and a 6 on a die roll. So here the interactive part. Is this random? Give me a raise of hands if you think this is random. And you think this is not random. Yeah. So this is the by now old-fashioned ant wars. So this is what you see on the TV when you didn't get reception. And this is random, mostly. There might be a encrypted signal from some pay-per-view channel here, but you can't really discern it. But it's mostly noise from the atmosphere in electrical signals. Roulette. Is this random? Who thinks this is random? And who thinks this is not random? Okay, I see a majority for random. This is not random. Because you are allowed to place the bets after the ball has been spun up. So if you can measure the speed of the ball and the speed of the wheel and the position of the wheel, you can pretty much get an accurate reading of where the ball is going to land, in what part of the wheel. And that means you can beat the house in the odds.
You can measure the entire universe. You can also see what the white noise will be on the TV, right?
Not really, but that's a physics issue. Yeah, there's some, but that's down to physics, and I won't go through that here. But this is not random. So we have standard random device. Who has used standard random device? Yeah. This is part of, or dev random if you're using a Linux system. Is this random? Give me a raise of hands. A few hands. Is this not random? Okay. This is random. Unless it's not. I'll get back to that. Rand, this good old C rand. Is this random? No one says random?
Depends.
It's not random.
Depends on the seed.
It's still not random.
But if the seed is random?
Then C rand is not random either. It's still deterministic. But it's also random because C rand is quite undefined in that sense, or unspecified. So you don't really know what you get anyway. Standard MT19937, or Mersenne twistor algorithms. Is this random? Give one random. Who thinks this is not random? More hands, yeah. This is not random. No, it's supposed to be random. So, but we use random numbers in many different applications. I guess the most common ones is for gambling or numerical simulation. But you also use them to generate your crypto keys, selecting things by random chance. You want to use testing to fuss up your tests or just generate a lot of random data. For games, you want your opponents to behave unpredictably. And for AI, if you want to generate something random. And these different applications use different properties or desire different properties. So for cryptography at least, you want secure random numbers. So you don't really understand, you can't predict them. If you're just selecting things, yeah, you want to be secure, you want to be trusted and unbiased, so people can't just hop into the right queue if you're selecting queues by random or something like that. If you're doing testing, yeah, you want independent and reproducible, because you don't want your tests to fail because some other test is running at the same time, or you don't want to test to see why did it just fail so you can reproduce the error. Gambling, yeah, you want secure, unbiased, and trusted, so it behaves as it's expected, and people can't exploit you. If you're doing games, yeah, you want to do independent, reproducible, and fast. So you don't have to send all the random numbers over the network, for example. You can just send the seed, and everyone can use the same random number generator independently and reproducibly and fast. AI, they just want to do fast. They don't really care about anything else. And simulation, yeah, you want unbiased, high quality, fast, reproducible, and independent random numbers. And I work here. That's why I'm talking here. And we have different types of random number generators in our computers. We have specialized hardware. We have secure random algorithms. We have pseudo-random algorithms. These three I will come back to. And then we have some other types here. We have quasi-random algorithm, which is more random than random. We have heuristical algorithms, which is more or less that you have a bunch of information, you just hash it, and you get a number. It's random. And you can also use pre-computed tables like this. This is from a republishment of an old book, 1,000,000 random digits. And it's quite useful if you just want to have a few random numbers. Just pick a rule how to pick random numbers from this, and then you get a sequence of random numbers. And it's quite good, actually. But for hardware sources, software is deterministic, so we need special hardware, often in your processor. But we need time to gather enough noise to create your random numbers. You can also use lava lamps like Cloudflare used. Just take pictures of a bunch of lava lamps and hash it, and then you get a random number. And then you can use that to make your cryptographic keys. But you can also just use your standard processor using standard random device. But this is implementation dependent, and not all platforms have a random device. And by standard, you can get non-random results from a normal random number generator. And you also have secure random algorithms. And the goal of these is it's hard to predict the future random numbers, even if you know the internal state of the random number generator or the existing random numbers you already produced. And this is needed if you might have an adversary that has something to gain by predicting your random numbers. So if you want to secure your cryptographic keys, if you're doing gambling or random selection, yeah, you want secure random numbers. And then you come to the big thing here. This is pseudo-random numbers generators. So something that looks like a random number generator but isn't. Often abbreviated PRNG. And these have 4 basic building blocks, more or less. So you have the state, which is the information the random number has on where it is, or the current ending state. Then you have the seeder, which you use to initialize the state. Then you have the transition function, which generates the next state from your current state. And then you have the scrambler that converts state to a random number. And you generate a random number by first seeding the state, then advancing the state, then scrambling the bits of the state you have to create a random number. And for the next number, just repeat advancing and scrambling, so on. And the basic algorithm here is that you have a state. This case is 4 bits. And you have a next state for each state. And you can have the code there for the next state. And the generator transitions the state to the next in sequence. And the period is the number of steps you need to take until you're back in the initial state. So if you reorder this, you get something like this. Yeah, the state is random. And you have a period of 8. If you have a worse algorithm, such as this, you want to step through all the possible states you have. And you want to avoid generators that have a shorter period, because then you might not reach all the states. So in this case, if you reorder this by just reordering it, you can see here that if you start at 0, you will come back to 0 4 times. And you won't reach the states in the lower half. So here you have a state of 4 bits and a period of 4. And then you have the scrambler, because as you saw in the previous one, the state is not always random, because it's just an algorithm. But you use the bits in the current state just generate a good random number from those bits. And the goal here is to create an uncorrelated, unbiased number with a uniform distribution often, and an int, a 32 or 64-bit int. And you can also use the same state to generate a lot of numbers. For example, if you're using SIMD, you can just produce a bunch of numbers from the same state. If you have enough entropy in it, just feed into your SIMD instructions. And then you use these integers to transform them to other distributions, if you want to use floats, or if you want normal distributed numbers, or another range, or something like that. And you seed this state by using a seed, which is a small number, often, much smaller than state. And this means that if you have a bad seeding algorithm, you can reach the same state from the different seeds, or adjacent states, so you just start one ahead of the previous state, and that means that the next random number generator will be the same as the other random number generator. So you need to take care about how you seed your random numbers. A good practice is often to skip the first numbers after seeding, because they are less random often, and avoid overlapping sequences. And some good generators can actually fast forward 1 billion numbers quite easily, just doing some clever math. And that means you can get independent subsequences of the entire sequence. If you have a sequence of 10 billion, you can just take 1 billion each in each sequence, and they will be independent of each other, and there's no risk of overlapping until you run out of your subsequence. Then you'll start to nibble on your neighbors. And this is, why should I care about this? You care about the performance. You care about the statistical quality of your numbers. If you use multiple threads, if you have concurrent users, if you want to reproduce your results, or you care about security. So why should you think about this? And you have a few different generators. So this is a quite simple one. This is called a linear congruental generator. This is the third type of generators used. It's fast. It's very simple. It's more or less a multiplication and a modulus. But they are often of very poor quality and have a short period, often, 2 billion in this case. But this is a standard generator in CRAND, some implementations. C++ has it as minstered RAND, and Java also uses this as the random number generator. but also in a lot of other places. So this is a nice list of, but they differ a little bit in which multiplier and which increment and which modulus it's used. And then you have the Mersenne twister, which is the most common random number generator used in the last 20 years or something like that. It's fast, but it takes a slow branch every nth number. So every 620th number, it will take a slow branch and generate 600 new numbers, and then it just returns a number each time and just scrambles it a bit with XORs and shifts, and then it returns a number and increments this index. This means it will have a very long period. So 10 to the power of 6,000 zeros, or a lot. It's an okay quality. It's not perfect. But the big downside here is that it's a huge state. So for every generator, you need a state of 2.5 kilobytes. And if you are in a state-constrained system, as an embedded or a GPU, you can't use this. But this is the standard generator in some implementations of C++, in Python, MATLAB. Julia has had it until they swapped. Excel also uses it, and a lot more. If you talk about a pseudo-random number generator, this was what people often refers to. But then you have more modern generators, 20 years or something like that. But they are very fast. They are very good quality, actually, even if they're very fast. They can have a very small state and even get good quality. And you can tune them for different applications depending on which instructions is the fastest in your platform or something like that. Or if you are using floats or ints or 64-bit numbers or 32-bit numbers, you can use an appropriate generator. But you see here, the code is also quite simple. It's more or less an XOR and a shift with different constants, and you just multiply it with a magic number, and then you have your number. We have also a lot of other random number generators. You have the XOR Shiro family, which is used by Julia now. You have the PCG family, which is used in NumPy. And you have random 1, 2, 3, which is going to be available in C++26 as the Philox 32 and 64-bit generators. So these are good choices if you just want a good generator. One of these. Choose what suits you. And then we have standard random, or standard rand. This is now considered harmful. You can see the example program. Can you see any issues there? What will it return? It will return an error, of course, because you're just returning. It probably won't return 0 anyway. But you see it, and then it has a global state. That means all threads use the same state. The implementation is unspecified, which means that it's not portable. It's not required by the standard to be reproducible, so you can get whatever you want. Implementations vary in quality a lot. It's actually slow, but it's also used by random shuffle, so avoid random shuffle also. And we test these random numbers by using tests, more or less, but we use statistical tests, and a lot of different tests, and we know what the expected result is of these tests. So we just run these tests a lot. We use a bunch of random numbers for a few hours, and then you can get your results, and you see, min standard rand fails the simplest test, and all the easy small linear congruential generators all fail this in different numbers. The Mersenne twister fails the big crush test, which takes 10 hours on a modern CPU. But modern generators doesn't. They are statistically random for all intents and purposes. There are other tests you can use. And one good thing to remember is we have a superpower. We are very good at noticing patterns. So look at your generator yourself or the generated output of your program. Does this look random? Do I see any patterns in this? If I generate random noise, do I hear any patterns that sounds funny or something like that? Because you can have very subtle problems. Question?
Yeah, so, I mean, quality, is that one-to-one with passing this test? Or are they two separate things?
It's an indication of quality, this test, because these types of tests are more or less designed to find bugs in generators that you have quality issues with your find patterns in your random number generators. For example, you can run a poker game and see how many hands does each player win if you change number of players or something like that. You can read up on the test U01 has a good bunch of tests you can read up on if you want. And then we have our standard random header. It's new since C++ 11. It contains random number engines, a bunch of random number distributions that you can use, and some other useful things for seeding, for generating canonical numbers. You have random device here. You also have standard shuffle in algorithm that uses a good generator. So use that one. And you have a bunch of different generators or engines. You have the min standard one, the merge and twist one, you have ranlux, you have the Knuth, and now since C++26 you get the Philox 32 and 64. And of these, only the Philox is probably useful for simulations. Otherwise, it's too bad quality. And yeah. But you have your int, and then you want to use it for something. Because the random number generator will just give you an int between 0 and a maximum value. To generate a bit between a range of A and B, you shouldn't use modulus and just with your range, and because these have some subtle issues, because the distribution of these will not be equal, so the larger numbers will occur less often. And you can also think about, if you have a small range here, you say 2, I just throw away all my randomness. I just look at one bit in the random int. And there are examples of generators producing 0, 1, 0, 1, 0, 1, 0, 1, 0, 1 in the last bit because, yeah, bad implementations. So what you should do is use a uniform int distribution, which gives you a uniform int between A and B, inclusive, because otherwise you can't generate the top number. You want a float between A and B. Don't just cast your random number int to a float and then divide it and then add it or something like that. Because then you throw away a lot of the randomness, and it's also some subtle issues with the distributions you can end up with. You can't, for example, here, generate 1 or the maximum value because you can't generate an int of max and so on. And also use a uniform real distribution. But the random header also have a lot of other useful distributions, so you don't have to code it yourself. You have the binomial distribution, you have normal distribution, you have Poisson distribution, discrete distribution, and many others. So use these if you want to use your random numbers, even if you create your own generator, because it's possible to create your own generator and use the standard distribution functions. And then you have my opinions on which generator you should use. If you are just lazy and don't want to type a bunch of numbers in your test cases, use min standard rand. You don't really care about the numbers anyway. Just want to be some numbers and you don't want to type them out yourself. I care a little bit. Use Mercy and Twister. I don't want to be hacked. Use a secure random number generator or a hardware generator. There's nothing in standard except random device. There are some libraries providing good secure random number generators, SSL, so on. I don't know. This is not my field. I care about the random numbers, how my numbers are. Use a modern random number generator and test it. This is important. And then you're going to pick your seed. That's the next part. So don't use time, because it's not predictable, because it often returns the current second. So if you have two users starting at the same second, they will get the same random number generators. Don't unnecessarily reseed. So don't call your seeding and then get a random number, call your seed, get a random number. Because it's often the slowest part of your random number generator, and they produce less random results. So don't do it. Make sure you don't end up in bad states with short period. Pretty hard to understand, but don't do it. Use something unique and persistent that you can find. Use the username. Use the test name. Use the thread number, the job ID, so on. Something that you know. And if you need something that is hard to predict, combine it with a strong random number or your random device or the current nanosecond. It's often good enough in the sense that it's very hard to attack this algorithm because it's hard to predict that thing. And if possible, fast forward so you get unique sequences per thread or user. And then we have some bad examples here. This is about IBM Randu. It was labeled truly horrible by Donald Knuth. It was used in some IBM mainframes. And that means that a lot of the early computational scientific results are affected by this if they use random numbers. Because three numbers in the Randu, three subsequent numbers are correlated. And if you take a fourth number, you hide the issue. So this is a random image I generated from a normal distribution using 4 numbers. This is if I use 3. And you can see what causes this if you look at 3 numbers. So if you have 3 numbers from the Randu, they will line up in these planes in 3 dimensions. So, yeah, this is an issue. And then we have a modern example. This is why I'm talking to you today, because that's why I had to read up on random numbers, because we've exposed this bug in our code. And this is from NVIDIA QRAN, which is the standard random number library for CUDA on GPUs. And they are initialized using QRAN init. You give it a seed, which subsequence you want, and an offset in that subsequence, and then you get the state. So you have the same seed for all threads, and you pick a unique subsequence for each thread, often, and you just have an offset in that thread if you want to advance something. And they say in their documentation, at least, that sequences generated with the same seed and different sequence numbers will not have statistically correlated values. And how many believe that? We believe that until we started seeing odd things. And it was things like we changed the number of random number numbers we used, we got completely different levels of noise. This is weird. We changed different orderings of different functions and so on. And then a colleague of mine was able to write this small program, which I then distilled even further to slideware. But this is the gist of it. So you use curad init to seed your random number generator, and then each thread then computes a position and you just add 1 to that position in a vector. And you store each sequence or each number in the sequence separately. So you generate a sequence, or you generate a normally distributed number, and yeah. But you see here on the right that for the far right at least, you have the blue, which is the mean of all sequences. And then you have the red, which is first number in each sequence. So you see that it's quite noisy. And if you look at the value in the middle, so in the top, the biggest bin, you see this pattern in the averages and the noise. And this shows that we have a correlation. So the threads have correlated random numbers, but they are very subtle. But it affects the noise level a lot. So if you don't use the documentation, if you just change offset to thread, so each thread uses a separate offset, we get this. It's fixed. In the end, we just threw this random number generator out and implemented our own, or based on a modern random number generator. So, some parting tips in the end here. Use an appropriate random number generator for your platform and application. You can gain a lot of performance, and head scratching can be avoided if you use a good random number generator. Transform it correctly to whatever you're going to use it as. Test it so you don't end up in correlated hell. And avoid standard rand and random shuffle. And to end, here's a random image I found on the internet. Any questions? Yes?
What about portability of all the random generators and distributions? Quite often, if you, for example, make a game and want to port it to different platforms,
yep.
You would like the same seed to generate the same level, for example.
Yep.
While you have generators that are behavior that is usually similar, for example, if you use a Merson twister, the distributions are not portable across standard libraries. Do you have any opinions on that or recommendations on what people should use?
It depends. I think you should be a bit careful how you use your random numbers then. So if you care about the distributions, don't use floating points, because that will differ between integer math is probably quite portable, but floating point math is not. And you have different optimizations and so on that you can turn off to get predictability in your code. Portability, yes?
Do you have any thoughts or opinions about stuff like noise random, like Berlin or stuff like that? Because I know it's pretty old. I looked up Berlin, it's like from the 30s, but for some reason we figured out in our game back in the day when I was in there that Berlin was way cheaper to get somewhat pseudo-random compared to like Merson Twister.
Yeah, so it's Merson Twister is slow in that sense, and it's also unpredictable. So, but it's hard to beat these modern generators where you more or less use 6 instructions to generate your random numbers. Yeah, I'm not entirely. It's not my field. Let's say it like that.
I believe there's a license issue, but I could be wrong.
Okay. Anything else? I will thank you and hope you have a nice evening.